Hello, ladies and gentlemen. This is Mr. Hunter, and this is part 2 of your electrostatic notes. So previously, we talked about the electrostatic force between two charges. We also talked about charges are conserved, which means they're quantized, and that means that they exist in whole numbers of the elementary charge. So I can only have 3 electrons or 4 protons. I can't have half an electron and half a proton. We also talked about the difference between electrons and protons. Now, around each of these electrons and protons are these electric fields. Electric fields are like auras around the charge, and they affect other charges in electric fields. So other charges and electric fields. So we already talked about this in class, but this will get this into your notes. So other charges and electric fields. So opposite charges attract and similar charges repel. And here's why. It's because their electric fields are really pushing on the other charges or pulling on the other charges. So for example, when I have a proton, remember our model of a proton is the circle and with a plus inside. So we have a model of a circle with our plus inside, and the electric fields always go out of protons, always. That's the model we use. Once again, remember, we can't see this stuff even with our current technology, but we can see its effect and observe behaviors. And so our model is that electric fields always come out of protons. In a similar fashion, with the electron we use as, I don't know why this line is here, but oh well. With the electron, we use a negative circle to represent the electron, and electric fields always go into electrons. So it always goes into electrons. Now these fields exert an electrostatic force on charges. And so that's what causes the protons, or sorry, excuse me, the electrons to actually move, because they are being pulled and pushed by the other auras around them. So now I'd like you to flip over to the back page, and I believe we're in the third column, because we're going to talk about what electric fields with a proton next to a proton. Or in this case, we have a proton next to an electron. So if I have, let's see, move that here. No, not move the page. So here I have a proton next to an electron. And sometimes the way I like to draw these is, as we know, the electric fields come out of the proton, and they are attracted to the electric field lines of the electron. Now, does the color really matter? No, I'm just trying to demonstrate that, once again, these electric fields come out of protons, and they go into the electron. So this guy gets connected here. This guy gets connected here. So that's why opposites attract, because their electric field lines kind of pull towards each other. And so the same thing for a proton next to a proton. If I had a proton next to a proton, as we've discussed, the electric fields move out of a proton. So here's a proton, and as it's heading out, it detects the other field line and pushes away. So they never touch. Why? Because both of these lines are positive. So they'll actually never touch. And case in point, I've talked about this in class. This means that the electric field, which we use the letter E, equals 0 newtons per coulomb. In that spot, you are invisible to electricity or charge because the electric field is zero there. So if you were like standing out in a storm and you were between these two protons, you would not ever get struck by lightning. So now we have an electron next to an electron, and it's going to do similar to what the protons are doing, with the exception of, as we discussed, the electric field lines go into electrons. So they're coming down and they detect the other field line and they push away from it because they don't like it. Because electrons are self-hating, they don't like each other. Okay, so notice the field lines never cross, and once again, the area in between these two electrons gives me a zero electric field, which is 0 newtons per coulomb, because it's a measure of the unit force per charge, which we will practice shortly in class. Okay, so 2 more concepts and we were done. Now, what I would like to briefly show you about is conservation of charge. When 2 objects touch, which this is called conduction, the charge is distributed evenly between the 2 objects. When they separate, the charges get balanced between the 2 objects. Let me show you why, and then I'll show, let me show you how, and then I'll explain why. So on this one sphere, I have plus 3 coulombs, and on the other sphere, I have plus 5 coulombs. When I touch them together, I actually have a total charge of 8 coulombs between these 2 spheres. Now, when I separate them, they each balance out to 4 on each side, and here's why. Basically, there is a ton of protons on each of those spheres, right? And as we know, protons don't like each other. Because the protons don't like each other, they push away from each other equally. And so since they can space out equally among them, then these spheres will always become equal. And that will always be the case. Because let me draw it in terms of pictures, right? Let's say that I have plus, plus, plus here, right? And here I have plus, 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 plus. I have 5 on this side. Well, when I touch them together, I have 3 black pluses and 5 red pluses. Oh, I should have split them up, like here, here, here. And let's bring these guys over here. So, among those charges. But what ends up happening is they evenly split out because they don't like each other. So I have, and actually at this point it doesn't even matter the color, but I have plus, 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 plus. Yes, technically some of those are red or some of those are black, but they're all protons, and so they equally push each other away. And so that's why charge is always conserved in the fact that the charge is spread out evenly because of the same charge, and they push each other evenly away. Like if you remember John Travolta in the Stations, when you got a ton of electric charge on him, a ton of electrons, you should have noticed that the electrons all moved to the edge of John Travolta because they were all trying to push away from each other equally. So now we get into insulator and conductor and induction and conduction. So an insulator is a material where charge cannot easily move. Material where charge cannot easily move. See if it lets me actually turn this into text. Close enough. So it's a material where charge cannot easily move. It is an insulator. A conductor is exactly opposite of that. It's where charge can easily move. So copy. I need a paste option on here to make this easier. So it's a material where charge can easily move. So some types of insulators. Um, Wood, let's see, paper, and rubber. Really good insulators. The charge can't really move among it. And then types of conductors, any type of metal. Water is a huge conductor. That's why you don't stand in a pool when it gets hit by lightning, because that charge moves to your body and will kill you. So that's why we don't do that. Okay, induction versus conduction. Induction is you charge without physical contact. Case in point. Charge without. I really like that Rakim showed me that. Okay, so induction is charging without physical contact, and conduction is charging with physical contact. Charge with physical contact. The example that I want to give you is when the first predictive observe explain I did with you guys, which was I was using Thumper to charge a rod, and then I held that rod close to a Mountain Dew can turned on its side, and the can started to move. When I was rubbing the rabbit fur with the acrylic rod, that was charging by conduction, because I was literally ripping the electrons off of the fur onto the rod. And then induction is charged without physical contact. So I never really changed the overall charge of the soda can. It was always neutral. What I did do is I polarized it. So polarization. So charge moves how do I say it? So polarization is the charges move on an object and they make it one side positive and one side negative. So charge moves on an object making one side positive and one side negative. So that's what we typically did with that can. Like we charged it by induction, which AKA we made the charges move by presenting other charges. So charge moves on an object, making one side, there we go, moves on an object, making one side positive and one side negative. And one side negative. Good job. So that is, in a nutshell, all that you need to know for electrostatics. So I will see you in class with this.